40 under 40 data scientists by Analytics India magazine for 2 years in a row, 2019 and 20. As an inventor, has filed five patents in different global locations. He is an author of 5 books. His first book has been recommended in HSLA Center at the University of Pittsburgh, PA, USA. His 4th book, that is PyTorch Recipes, was published by Press and added to Buswell Library, IL USA. His 5th book, that is Practical Explainable AI using Python, was recently published by Press and has been recognized as a textbook to Barcelona Technology School Big Data Analytics course. He has delivered a keynote sessions at the Global Data Science Conference 2018 CA USA. He has delivered 500 plus tech talks on data science, machine learning, DL, NLP, and AI in various universities, meetups, technical institutions, and community arranged forums. He is visiting faculty and academic advisory board for AML in MTech in AI course and cybersecurity course at Rewa University, Bangalore, India, and also various other universities. Has mentored and trained over 2,000 plus data scientists and AI engineers in last 9 years. So I think the participants will really be benefited from Dr. Padita Mishra's expertise and his insight in AML. So I welcome Dr. Padita Mishra to start his session, but my request just to give 5 minutes. So before that, Dr. Aditya Kumar sir, he will be presenting, will be giving a brief intro about his the project that he is going to carry out, guide the participants. So I invite Aditya Kumar sir to kindly brief the project that he is going to guide. And after 5 minutes, Dr. Padita Mishra can start his talk. Thank you very much. So Aditya Kumar sir, please give a brief on the project you are going to guide. Thanks a lot.
Sir, I think Aditya Kumar is going to join, so maybe we can start.
Okay.
And
then
later
sir,
he can.
Paditya sir, Dr. Paditya sir, so may I request you to kindly start the session. So the participants, so please give a warm welcome to Dr. Paditya sir, who will be now taking the session. Thank you all. Paditya sir, please.
Thank you. Thank you, everyone. Can you hear me? Am I audible, Abhijit? Am I audible?
Yes, now we can hear you.
Can you hear me? Okay, great, cool. Okay, thank you, Dr. Manas, for the introduction, and thanks everyone. And we are going to talk about today introduction to neural networks, and I think this is a very fundamental, or I would say very foundational topic that we are going to talk about, which is a basic thing for any aspiring AI/ML scientist. Just understand how the network works, and so I can quickly go ahead with the topic. And how this session is being organized is that first I'm going to talk about the basics of it, and I'll just skip my introduction. That's what you have already covered. So to understand the basics of the neural network, understand the structure of the neural network, so how it exactly works, etc. So I think this will give a lot of clarity. And apart from theoretical, I'll not get into a lot of mathematics of it. or the mathematical foundations for how this computation happens, or the nitty-gritties of the mathematics. But I'll emphasize more on the programming side of things, right? So little bit of theory, little bit of programming side of things, how this can be implemented using Python, and also some of the playgrounds or automated systems or frameworks which are publicly available, which we can use just to play around the neural network structure and all to understand how exactly it works. And subsequently, I will also going to share some documents, which are like some open source contents, just to understand further into the neural networks and its modalities. Okay, so because everything cannot be covered within 1 hour, so I would like to keep it very basic, small, and I will also share the contents so that students can again read or study further to expand their understanding about neural networks. Okay, so with this, I think we can start. Okay, now what is neural network? Before going back to what is neural network, and see, this is not a new concept. Neural network was there since long. Maybe I can say, let's take more than 30 plus years. It is there in the textbooks. And like many people, they have also implemented in 1976 when Geoffrey Hinton created the neural network as a one hidden layer and submitted as a PhD thesis. And first time his thesis was being rejected in US University because this is considered as practically impossible to execute in any programming framework or using any programming languages. So it was declined. And then further, he continued his study or research around neural networks and how to make it work. Later on, he relocated to Canada and Toronto University, and he thought of how to make it into production. So again, and all that is right now is history. So what he has created in 1976 is something which we are implementing in various systems today, and we are creating learnable systems. Now, what is learning? Learning is about remembering the historical patterns, the historical relations between various data points to observe what happens and why it happens, and using those kind of historical patterns, how we can make a prediction for the future, right? Because today, if we are trying to create some predictive systems, right? So the predictive systems are nothing but like it can be classification, it can be regression, it can be clustering. So all are basically pattern based. Now for pattern recognition and making predictions about the future, so what is required is that you have to understand the right features. You have to emphasize more on creating intelligent features so that those features can be utilized to create predictions. Now, formally, we cannot create all such features on our own. Why? Because of some complexities. What are those complexities? Non-linearity in the data, which is a reality. In traditional statistical systems, when we look at the predictions and when we create those features to generate predictions, so we assume that the features or the data, it follows a normal distribution, which is a Gaussian distribution or properties of the Gaussian distribution, which is practically impossible today's world. Because today, whatever data we are seeing, hardly there is any linearity. It's all about nonlinear data. So in the presence of a nonlinear data, traditional methods of linear models becomes like inefficient in terms of making predictions or classifications, etc. That is why we would need highly scalable nonlinear system which takes into consideration all the modern world complexities around the nonlinearities. That is why the neural network came into picture. Now, the other complexity is that if you can create handcrafted features manually, then also there is a possibility, but it is impossible in a high dimensional scenario. What does that mean? Okay, let's take a simple example. So you want to predict something, there are two features only, x1 and x2, and you are predicting something, you are getting an accuracy of certain level, like let's take 60% and 70% accuracy you are getting. But that's not the best accuracy. In order to achieve the best accuracy, what you can do is maybe x1 square or x2 square. So two additional features, which is like square features you want to add. Then subsequently, you can add some interaction like x1 multiplied by x2 or x1 plus x2, which is multiplicative features or additive features you have to introduce to your model. right? So if you have 2 features, you can think of probably 6 set of features which you can use to make predictions, right? But this becomes extremely complex when you are operating in a like 100 plus features, right? So 100 plus features, what are the possible combinations? Is it always going to be square into square, or square into cubic features, or cubic into some other features? It is a lot more complex. So we cannot compute by simple like manual way. We cannot handcraft those features. That is why the complexity of nonlinearity you cannot introduce to the model by creating those handcrafted features. You would need an automated system which can create those complex features on its own and introduce into the model and make predictions, right? So that is why the neural network become very popular, especially in 2012 and 13. Neural network came into picture with the revolution of this open source world, because earlier it was only one mathematical software, that is the MATLAB. The MATLAB was having the neural network as a model which you can create, and it was supporting up to 200 records only. You cannot do more than 200 records in neural network training, even like beyond one hidden layer. It was absolutely impossible, right? In 2013, R software was becoming very popular, and R had a library. It was called NNet. Using NNet library, again, you can derive those weights of a neural network and you can implement it. But again, that is also subject to certain levels of data. So you cannot go beyond 1,000 records or 2,000 records, because once you optimize the 1,000 records, 2,000 records, our software will crash. So it was not optimal. Similarly, in 2014, Python came up with a neural network library. Again, subsequently, there are a few more frameworks get identified, which is like TensorFlow came in 2015, Keras came in 2016, and PyTorch came in 2017 and 18. So that's how the evolution started, and it keeps on. The neural network become prominent, and it becomes the mainstream programming like way. And subsequently, people have developed a lot of frameworks around the neural network structure. And probably now you can see almost all the statistical softwares, they support neural network as a model. Okay. Now, going back to the understanding. So first, I was just trying to explain why neural network, right? And second, now we have to look at what is neural network. So neural network is just like there are some connections, right? So I'll just give you some simple analogy. Let's take you are going to a mall and you are seeing somebody there. You try to recognize where I have seen this person, right? So you will have different features, right? So you will think about, is this person belongs to my village? This person belongs to my school. This person belongs to my college, or I have seen he's my colleague in previous organization. So you'll start exploring all the features to figure out who is this person, right? So it works exactly the brain's biological network works, right? We are trying to understand who is this person just to recognize and recall his name and just to say hi. Automatically, our neurons, they try to connect through the different layers to recognize who is this person. Now, while establishing those connections, you are multiplying different weights that you have learned over the years, right? And there is a remembrance layer, because you will associate somebody with some events, some places, some common friends, some entities like institutions, colleges, schools, so something like that. So you have to connect those features to something just to recognize this person, right? So what are those weights? The weights are nothing but the relations, right? Suppose me, okay, I know Mr. A through my college, right? And I know this person, he was my classmate in school, then in college, then in my postgrads. So there are 3 established connections to recognize this person. So I can quickly recognize this person, right? So exactly the same way the neural network works. And to organize this neural network through a proper structure, how the structure looks like. So it's like there is something called input node, there is something called output node, and there is something called hidden node. So there are 3 layers we should look at when we think about neural networks: input, output, hidden. So what is hidden? I'll come to that later, right? So first, let's look at what is input and what is output. Okay. Now, in machine learning or AI, what we try to do, right? And why it is different from the statistical systems. So if you look at the statistical systems which we use to make predictions like a linear regression, so mx plus c, we can just use as an equation, right? The equation is a fixed equation. We have input, we have output, and there is some relationship, and that relationship is reflected by the equation mx plus c. So which is a constant, and the equation is a static equation. And if the equation changes, the weights of the equation changes in future, we have to manually compute it and upgrade the equation or modify the equation. That's how the system works. However, in machine learning, we want the system to automatically learn the weights and automatically update the equation, right? Sometimes the equation is not established. We don't even know whether it is mx plus c, mx multiplied by c, mx divided by c, we don't know, right? So we want the algo to identify what that equation is. If we can use this equation, and if we can identify this equation and its parameters, we can dynamically update it as and when the data gets refreshed, and we can make predictions better, right? So the objective of machine learning is that to come up with an equation which relates the input to the output. Input is what? Input is your data. Output is what you are trying to get from the system, right? So input is data, output is what you are trying to get as a result, right? And just take a simple example, your efforts. How much hours of effort you are putting in your studies versus what is the outcome you are getting is grade A, grade B, grade C, or CGPAs that you are getting. If you take all the historical data of people putting an effort, as well as doing physical exercises, as well as being part of sports events, as well as their health conditions, or maybe their parents' education or their demographic profiles. If I can collect the data of all the students of last 10 years from a college, and I'll collect their all the CGPAs, I can create a linear regression model over here, right? So what I can do, I can use this data to make a prediction, so that in future, if I can tell, hey, if you are going to put this many hours of effort, and also you are doing physical activities or playing a lot of sports and games, are being part of cultural activities, and this is so and so, this is how your CGPA is going to be, right? So we can create a predictive model out of it. That is why you can predict how your CGPA is going to be based on all those parameters. So this is just a simple example of introducing a predictive system, right? So how it exactly works, all the inputs are nothing but the features. So in this CGPA example, the hours of effort that you are putting in, the cultural activities you are spending, whether you are part of any political activities in the colleges or not. If some features would be positively impacting the results, some features would be negatively impacting the results, right? So if you are putting let's take 15 to 18 hours in the library, and beyond your, so let's take 5 to 6 hours in the library beyond your classroom sessions or classroom activities, definitely it is going to impact positively your CGPA score, and you will be scoring more. And if you are being part of a lot of cultural activities, political activities, which is non-study activities, definitely this is going to impact negatively to your CGPA score, right? So similarly, all those features where the student's effort is going, if I can just collect all the data as input features, and I can make a prediction on the output, which is how much CGPA I'm going to get, right? That becomes a perfectly predictive system. So in such a predictive system, you take input and your output data of last 5 years or 10 years, and you try to build a model. You want to understand which feature, how it is related to the output, right? This is simple predictive system, because your CGPA is, let's take, it's a grade from 0 to 10 or something in the range, right? So it could be continuous as well, because some CGPA would be 9.68, somebody could be 7.635 to 8, something like that, right? So if your target variable is numeric, and that becomes your regression problem. Now, if it is a classification, simple, it's a binary result, whether you will pass or you will fail, right? It becomes a classification. So your output will have 2 neurons. If it's a regression problem, your output neuron that you see, each circle represents 1 neuron. So The output in case of regression becomes one circle. In case of a classification, it becomes two circles if you have two classes. If you have multi-classes, let's take you have 5 classes. So you can imagine 5 different circles in the output layer itself, right? Similarly, in this system, you can imagine the inputs as well. The inputs are like 3 features only. Okay. So the objective here is in a neural network to understand the functional relationship between input and output. If we understand the functional relationship and establish the functions and the connected weights, each arrow here represents an weight, right? So the weight is just a multiplicative factor to the input parameter to compute the circle which is in the hidden layer. Now that becomes an interim layer. Okay. So I'll explain the mathematics behind it a little bit at a very high level, which is quite easier for you to understand how it works. Okay. Now, the NN or neural network is also known as artificial neural network. Why it is considered as artificial neural network? Because we are artificially ingesting some kind of external weights to the system, right? Now, these weights are something which somebody has not given this to us. How we are computing? Automatically we are computing. We are artificially creating those weights, right? So I'll show you a quick demo of how exactly the neural network is getting initialized and how exactly it works. Okay, then you will understand why it is called artificial. It's not a real neural network. It starts with artificial weights, and through iterations, it becomes more solid in terms of prediction, like performing classification or regression. And at the final layer, we will get all the weights which are real weights. Okay, those real weights, it represents the statistical relations or functional relations between input and output. Okay, so there are different kinds of neural networks, and those kinds of neural networks are connected to different use cases or different types of tasks. So at a high level, if it is a simple one hidden layer neural network, it is called a simple neural network, which means input, hidden, output. Now, if your data complexity increases, I'll also show you this as an example. Please try to concentrate here on the theory part of it. I'll exactly show why multiple hidden layer neural network is required, why single or simple hidden layer or simple neural network is not enough, right? What does that mean by data complexity? How the data complexity actually happens, right? So I'll explain those scenarios as well. So there are different kinds of neural network. Simple neural network, it's easy to implement. Even in Excel sheet also, you can update or you can create one neural network. You can introduce a VB code, Visual Basic Code, in your Excel spreadsheet, and you can perform the neural network. The complexity arises when you are introducing multiple hidden layers in a neural network, which you cannot compute it using Excel sheets. You need high-level programming languages to do that. One of the high-level programming language is Python, which or maybe R. Now today, there are other programming languages also which supports this, like Ruby and Scala. Also, they are coming up with neural networks. Okay, so yeah, so at a high level, there are 2 types: simple and multiple or complex. Then there is 2 more variants. One is called feed-forward neural network, which means it only gives the output to the next layer. There is no loop back. However, the back propagation is basically, it first goes through a feed-forward neural network, which means it computes, passes the output to the next layer, and it makes a prediction. There is some error. It passes that information to the another input layer itself. It goes as a bias and it gets introduced to the model. And this back propagation model automatically updates the weights again. So till the time this back propagation works, till the time it matches the input to output. If your input becomes exactly output, then your back propagation model reaches optimum step and you can stop there, right? So feed forward, there are some use cases where feed forward neural network would be useful. And there are some use cases where back propagation neural network would also be useful. Okay, now what is the key to the functioning of neural network is that activation functions. What is activation function? Activation function is nothing but the equation that we are trying to build or develop, right? So if I just look at this particular graph over here or image over here, so input, there are, let's take 4 different arrows here, which is connecting to 4 different circles in the hidden layer, right? Each arrow represents one kind of weight, a numeric value. What is weight? It's simply a numeric value. It can be in the range of 0 to 1. It can be in the range of whatever you define, right? A small numeric parameter, which is getting multiplied by the input parameter in order to arrive at this. Now, you want to apply activation function because you want to do a sum product of it. You will multiply it, sum it up, and pass it to the next layer. That is why you need an activation function. What is activation? Activation function is a functional relationship which converts the input to hidden layer, right? And hidden layer to output layer. So we call it a mapping layer when we go from input to hidden. We call it a demapping layer when we are going from hidden to output. Okay. And similarly, this is called activation function. Like each arrow represents a weight, and this weight is connected through an activation function. Okay. So the activation function here is, there are different kinds of activation function. Simple linear mx plus c, that can be a linear activation function. There can be threshold based activation functions. There can be sigmoid based activation functions. So sigmoid is nothing but a non-linear function. There can be RBF based, radial basis function based activation functions. There can be different kinds of activation functions. The most robust ones are the ReLU, which is called rectified linear units. And sigmoid is also useful in case of data having binary classifications, right? So some activation functions are easier, some activation functions are complex, right? So there are different kinds of activation functions which are being utilized just to convert the input to the hidden layer, and again hidden to the output layer. That is why we need the activation functions, right? So yeah, this is a little bit theory about the activation functions, and this is the architecture that we are going to talk about. So in this architecture, if we just look at, so here there are two inputs only, x1 and x2. Now, if I extend it to n-dimensional scenario, so here let's take m features are there. X represents one feature, xm represents mth feature in the data, right? And then comes the weight layer here. These are your input features. Here are the weights. Each weight is corresponding to each input feature right now. Now, once we get this weight vector, this is called weight vector, because all the weights will be connected over here. And there is a bias, little bit of bias. I will come to that bias thing later. Okay. So this is nothing but the residuals. The residual comes as a bias and it gets fed as an input data itself. That's why the bias unit 1 you can see here, this is part of the input values. Now this input values multiplied by the weight coefficients, it goes to the next layer as a function. Now this function needs an activation function. Okay, this sum product of the data that you are collecting, let's call it Z. This Z value is holding a function that has a linear relationship, let's assume for now. And this is a linear function, linear activation function, which gets applied on the Z value. And it produces another numeric parameter, which is called, you can call it alpha. So maybe the symbol is a little bit different, so I'll call it alpha only. Then you will apply another transformation function in order to generate it to the predicted class level in case of a binary classification problem. Now this layer, when you are applying this activation layer, this becomes your mapping layer. And when you are doing the reverse transformation to the prediction layer, that becomes a demapping layer. Okay. So this is the theoretical foundation of how activation functions work. And this is some of the examples of the activation function. This is called a threshold-based activation function. This is called a sigmoid-based activation function. So sigmoid-based activation function is relating to any kind of logic models or logistic regression models, which is basically nothing but the logic function. And also on this side, you can see the threshold-based function, which is a linear-based function, and which uses 0.5 as a threshold criteria. And if something is less than 0.5, it passes to 0. And if it is greater than 0.5, it passes to 1. That's how the threshold-based function works. So similarly, there can be multiple different kinds of activation functions. So what are the key takeaways from this? So the key takeaways from this is that in order to construct, first thing is, how do we translate, how do we translate the practical problem to a neural network problem? how much data we have to train a neural network problem, whether the data is linear or non-linear, what are the properties of the data, right? And deciding on various parameters. What are the various parameters? Activation functions. What are the different kinds of activation functions we could use? How much or what is the iteration that we are looking for? Because we need more computational power in the machine to do all such combinations, all such iterations to run. Okay, so let's go ahead with, I'm just switching my application to a Jupyter notebook here. Okay, so I'm just, you can just let me know if the fonts are legible, or I'll increase the size a little bit. Okay, so yeah, let's get started on this neural network notebook from here. So this Matplotlib library, this is just for visualization, data visualization. NumPy library is for numeric computations and generating random data. sklearn is for sklearn scientific. This is for machine learning performing. It's called scikit-learn. sklearn datasets, it gives you a lot of datasets to do practice. Linear model, it is a linear regression model from scikit-learn library, machine learning library. Again, Matplotlib, just importing the Matplotlib just to that's library. You need to import just to use modules from within this library. Then this Matplotlib inline, this is if you want to display the graph just below the command line here, you need to introduce this line, otherwise your graph will be suppressed. Only you can see the graph address, you will not be able to see the graph. RC params, it's just about the width and height of a graph that you want to configure for this entire notebook. So you can just set up the 6 and 8 as row height and column height of the graph, so that it fits to the screen when you are running a script. Okay, so that's about your introduction of a package imports. Now we will artificially generate some sample data over here. Okay, now looking at the data here, okay, np.random.seed, this is just to initialize a seed value which remembers how the data is getting generated. Here I'm just generating 200 records, noise equal to 2.0. I just introduce noise equal to 0.01. What happens? Let's see. No overlap. Noise equal to 0.01 means no overlap. This is possibly like a simple data set. Now, if I say noise 0.001, now what happens? Right? No overlap, and you can see the data pretty much clean. Now, if I introduce a little bit of noise over here, what happens? So data becomes little scattered. Now, if I increase the noise level, now this becomes extremely complex. Okay. Now think about the linear models that we spoke about earlier. Now, if I need a linear straight line here, which separates the blue dots from the red dots, is it possible? No, it's not possible. Why? Because of misclassification errors. Here, if this is the intended line we're trying to draw, which separates between the blue dots and the red dots. Okay, so what happens here is that you can see the blue dots here on the lower side. You can see the even the mix. So which means it leads to the error in the classification, right? Now, if I simply replace this with what? Noise, I will reduce it, make it 0.00. Okay. Now you want to fit a straight line over here, still you will get error. So basically this data is nonlinear. When your data is nonlinear, right, you cannot fit a linear model to the data. That's why, how do you want to fit a model over here? You want to fit a model over here which should be like this, which achieves 100% accuracy, which is also too good to be true, which means it's overfitting scenario. Practically, when some new data point comes in, your function will not be knowing how to classify it, right? So these are some of the complexities around the real world scenarios. So I'll keep it to only 20% right now with this example. Now, I'm simply training a linear logistic regression model with cross validation. And this is my X and Y. which means I'm just creating some sample data, 200 records. 200 why? Because just to quickly showcase this demo to you, when you practically implement this, please increase this to 2000 or 20,000, which will take some time, at least 15-20 minutes to run on your machine. So you should go ahead with that. Okay. So this is a simple logistic regression model, and I'm just trying to get a score. So score is 85%. So accuracy is fine. Now what I'm trying to do, I'm just trying to create a decision boundary plot. So in a two-dimensional graph, it is quite easy to visualize the graph. Right? So I'm creating a custom function over here. I'm creating a nested function over here, which takes the min and max, and also takes the range of a min and max of height of the points that it takes. Right? It takes the values from the predicted function, from the prediction function. Right? So this is a helper function just to create a graph. Okay. So, and what it does is nothing but it takes the prediction function, it stores the value in Z, and it takes the data and reshapes it and make it compatible for showing a scatter plot superimposed on the decision boundary. Okay. So this is just a helper function. Now, after that, what happens? I will just apply the function over here. So this is a logistic regression model. You can imagine 15% error over here. The red dots you can see over here. However, in comparison to the blue dots over here, the red dots are less. Similarly, in comparison to the red dots over here, the blue dots are less. Now that less is nothing but the 15%. So accuracy is 85%. However, the error is 15%. And this is due to the noise in the data, that is 20%, which is artificial data. Now, if I reduce the noise to 10%, what happens? Now we reduce the data to 10% noise, retrain the model, again compute the accuracy, now improve the accuracy by 4%, it is 89%. I'll run this decision boundary once again. Now here you can see less data points are being misclassified. Okay. So if your overlapping percentage of noise in the data increases to 40%, let's take, and you retrain the model, your accuracy drops. Now it drops to 82%. Earlier it was 85%. Now it drops to 82%. Now in this case, if you just represent it in a graphical way, what happens? Now you can see a lot of noise in the prediction itself. Right? So the objective here is the noise in the data or non-linearity in the data, if it increases, that makes the process more difficult in order to make predictions or classifications. That is why exactly we need to introduce non-linear functions. So now, instead of a logistic regression function, if I can introduce any kind of a non-linear functions, now what happens, right? That non-linearity is nothing but the neural network that we're trying to introduce. Okay. In a linear regression, what happens? X multiplied by weight plus bias, right? That's the linear equation. So let's take this logistic regression. It is nothing but a linear equation that we're trying to use. So this equation is called Z1. Let's take. Now, X is one input. W1 is corresponding, the weight 1 corresponding to the input plus bias 1. Now this functional relationship, it produces one output with the G1. Now you are applying an activation function on top of it. So tan H, hyperbolic tangential function on G1, it produces an output which we call it alpha 1, right? This alpha 1 multiplied by weight 2, which is corresponding to, I'll go back to the same graph once more. Let's assume this one is X1, this one is W1. So X1 multiplied by W1, on top of it you apply plus bias 1, on top of it you apply the hyperbolic tangent function, you get alpha 1. So hidden 1 is alpha 1. This circle is alpha 1, right? Now what happens? Alpha 1 multiplied by W2. So alpha 1 multiplied by W2, this arrow is W2. So this alpha 1 multiplied by W2 plus some bias B2, right? That on that result, that is called, we call it Z2. On this, you will apply another transfer function, right? Or activation function. This is also called transfer function. This is also called activation function. Now, since we are deciphering the output, we call it deactivation. So activation starts here, deactivation starts here, but today everyone calls it activation. The first one is also activation, second one is also activation. Now here you could also use linear. You could also use tangents, hyperbolic tangent, or you could use softmax. Okay, so I'll tell you why softmax is being used here. So tan H you can apply over here on G2. G2 is your dot product or multiplication of A1 alpha 1 W2 plus B2, which is this layer. You apply a transfer function or activation function on this, you get the predicted result y hat. So y hat is the predicted result, or which is called the output. Okay. Now, in this case, softmax is required because softmax gives you the probabilities associated with the two classes. Since it's a classification, there are two classes. If you use softmax, it can give you the class probabilities. If you don't want the class probabilities, you could remove the softmax and you could use linear, or you could use any other activation functions. Okay, so these four lines or those four equations are especially the fundamental behind neural network. If you understand these four things, it's clear. Okay, now how to compute those things, how the backpropagation works. So next couple of lines we are trying to understand right now. Okay, now before explaining the further layers, like how exactly the gradient descent works, what is gradient descent, right? How the learning rate impacts the gradient descent, how the regularization works, all those things we will discuss. Okay, I think I'll try to because I need some time to take you to this notebook. Okay, I hope it is okay with everyone, right? Okay, so let's get started. So training set size is X, which we have already taken, which has two features. Next comes neural network input dimension 2, output dimension 2. Let's get started with epsilon 0.01, which is the learning rate. How the learning rate impacts. In the optimization process, if we set a high learning rate, it may miss the global minimum point in terms of identifying the global minima on a loss function. What is loss function? So loss function is nothing but the error that you are computing, right? So this is a predicted y. You will have actual y on the training data. So you will plot the error function on a graph and try to find out the function that approximates the error curve and get the minimum point on the error curve itself, right? So the learning rate means it is a rate that especially tries to optimize or minimize the cost function or the error function or the loss function, right? So and also conceptually there are three things: loss function, cost function, error function. Loss function is free from regularization. If we are going to introduce any kind of penalty, which is either L1 penalty or L2 penalty, that becomes a cost function. So cost function equal to loss function plus regularization. The regularization strength, it depends on the parameter called lambda, right? Regularization, maybe if your data has high dimensions, you need to regularize this, so you can introduce the regularized strength. Okay, the learning rate is the objective learning rate is to upgrade the weights in such a way so that you will try to find out the minimum point on the error curve, right? The higher the learning rate, you may get the results faster. However, you may miss the global minimum point. If your learning rate is very small, there is no way you can skip the global minima point. You will reach there, but it will take a lot of time. So you have to identify what is the best learning rate. Similarly, you have to identify what is the regularization strength, right? These two parameters, it decides how the gradient descent algorithm should work on an optimization scenario. Okay, then comes, so the loss function. What is loss function? So loss function is nothing. I'm just initializing model W1 to W1, B1, W, B2. W1 is weight from input to hidden. W2 is weight from hidden to output. B1 is bias from input to hidden. B2 is bias from hidden to output. Now, first we are going to do forward propagation. In forward propagation, you do a dot product multiplication of weight 1 with X plus B1, you will get G1. Now A1 you will get when you apply the NumPy library we are using to apply tanh function, which is hyperbolic tangent function on G1, just to get A1. Now A1 dot product multiplication with weight 2 vector plus V2, we are getting Z2. Then we are applying the exponential function just to arrive at the exponential scores. Then what we do, we get the probabilities. So probabilities are derived by this function. Then comes the loss function. So we are getting the log probabilities, and then we are adding the regularization strength to the loss function, which becomes a cost function. Okay. Then prediction function. So this customized function, it does the predictions. Then this function, it creates or builds a neural network function, right? So first we do a forward propagation, then we do a backward propagation. In backward propagation, we are doing a like a derivative. So this mathematics, please, I will give you some content. Please go through the mathematics of it, because the back propagation partial derivative mathematics, you need to spend some time to understand how exactly it works. Then comes the regularization term, and here the regularization upgrades strength, which upgrades the gradient descent parameter updates. These are final set of parameters that is getting stored, and that's getting utilized to make a prediction. So this is your build function that we are going to get. Now let's take 3 node or 3-dimensional hidden layer we are trying to create, and print loss equal to true, and we'll train a model here. Now what happens with each iteration, right? So this is the error, 1000th iteration, this is the error like this, and how many times we are trying. So the epoch we can see here, where we set the epoch, somewhere we set it, right? $20,000 iterations, we set it somewhere. Let's look at somewhere we put it. Yeah, number of passes, 20,000. This 20,000 iterations we are trying to do, which is too high, right? And we can see the errors over here. Now, after training the same data, right? Let's look at how the function looks like. So it becomes a curve right now. Okay. This is a 3-layer hidden layer neural network, right? So if I increase the dimensions, now first I will take 1 hidden layer, 2 hidden layer, 3 hidden layer, 4 hidden layer, 5 hidden layer, 20 hidden layer, 30 hidden layer, 40 and 50, and subsequently, as I increase the hidden layers, right, it tries to capture all the non-linearities in the data, and my model becomes more complex, right? So as I add more dimensions or more layer dimensions to the model, my model becomes more complex. It captures more complexities in the data, and thereby it improves the model accuracy as well, right? So let's look at this. Okay. So first it takes 1 hidden layer, which is equivalent to your logistic regression model, which we saw earlier. Okay. So let's first see that. It will take some time because here we are running it in iterations, in loop. So we are writing a for loop to take 1 parameter as a hidden layer dimension from this particular list that we are picking up, right? Then it creates a subplot, build a model with 20,000 iterations it runs by taking 1 hidden layer, creates the decision boundary, and this decision boundary is fed by your predict module, which takes the model trained using the input data, it makes a prediction and it shows the result. Okay, so it will take another 5 to 10 seconds to run. Let's see. Okay, now it has come. Okay, hidden layer 1, which is simply a straight line, which is similar to logistic regression model. Now you can see it's a straight line. Hidden layer size 2. Now 2 hidden layers we have. Now that becomes a little bit curved, right? Now this becomes a little more complex. 4, it becomes more complex. 5, 20 hidden layers. 30. Sorry, these are not number of hidden layers. These 30 are neurons, right? Which means these are neurons, right? You have one neuron or one circle in the hidden layer, that becomes hidden layer size 1. Hidden layer, one hidden layer, number of neurons in the hidden layer. These numbers that you see here, hidden layer size 30 means one hidden layer only with 30 neurons, which means 30 circles are there, right? So 30 circles, 40 circles, and 50 circles. So here with 50 circles, you are achieving almost 100% accuracy here, right? These are like overfitting scenarios, which are extreme scenarios. So 50, I would not call it as a best model because practically it is impossible to implement. 40 also, I will not say it's a best model. 30 is also not, I'm going to say it's a best model. Probably 4 is the best because it's relating to the reality, which means it's not an overfitting scenario, right? How do I identify whether it is overfitting or not? So this is a training data example. Now, if I can extend it to, let's take some test data, I'd be able to see how much prediction it is actually making, right? So if a training accuracy versus test accuracy, there is a deviation of around 2 to 3%, then it is fine. But if it is beyond 2 to 3%, then it is an overfitting scenario. In those overfitting scenarios, we have to retrain the model or fine tune the model. Here we have taken only hidden layers, right? Number of neurons in the hidden layers. So we can introduce or we can play with other parameters as well. What are those other parameters, right? We can play with activation functions. We can play with regularization parameters. We can play with learning rates, etc. And we can also play with the number of features. Currently it is 2, and we can, that is the input dimensions, and we can introduce more input dimensions, right? So that's how the neural network model works, which practically, I mean, writing a code, I'll just share this notebook as well. Please go through it and run it. Okay. Now, if I just relate it to another scenario, there is an online application, please go through it, which is called playground.tensorflow.org, which is provided by Google. And this is a very good platform where you can experiment. I'm just putting that in the chat window. Please bookmark it on your machine. Okay. Now let's look at how it exactly works. In our code, we say number of passes, which means iterations. That is called epoch. Epoch is number of times or number of iterations you want to train. Okay. Learning rate, there are different kinds of learning rate you can choose from here. Higher the learning rate, that is 3, 10, 1, you choose, it will process the data faster, right? However, if you choose a smaller learning rate, it will take a lot of time to train. Okay. Activation function. There are 4 activation functions currently over here. If you are writing Python programming, you will have more choice for choosing more activation functions. The popular ones over here: linear, which is typically used in the output layer; sigmoid, which is also typically used in the here you can see softmax is not present. Softmax is required for classification because you want to get the probabilities, right? So this application is just for learning purpose, and this is not for production. This is just for your understanding how exactly it works. Regularization strength, L1 is lasso, L2 is ridge. Lasso, least absolute shrinkage selection operator, which means if your data has high dimensions, data sparsity would be very high. In order to reduce the sparsity, you could choose the L1 as a regularization. If your data has some kind of a multicollinearity, which means the features may be or could be related like with a high correlation value, you can introduce L2. L2 is known as ridge, right? So L1 penalty or L2 penalty you can introduce as a regularization. And also you can introduce the regularization strength, which means similar to learning rate. You can introduce zero regularization, means it is simply linear model. That means no regularization. If you choose something which is not equal to 0, which means you are applying regularization strength to the calculations. And problem type, you can choose whether you want to train a regression problem or you want to choose a classification problem. So let's go ahead with the classification problem. So these are your input parameters that you should introduce to your model to train the neural network model. Okay. Now setting the data. Now here, this step is giving you the data generation step. You can choose a simpler data set, like it's already classified. You just have to build a function. You can put a linear straight line over here. It is easy to classify. Okay. You choose a complex data like this. It requires a function. The system needs to define a function which you can use to make predictions for the future, right? Now here, this part you can just increase or decrease, like a ratio of a training to test data. Let's take 70% of the data I'm going to use for training and 30% I'm going to use for test. Noise you can introduce. You can introduce high noise to the data. You can introduce low noise to the data. Let's noise at 20% only. Batch size, this is important because you cannot train the whole data at one go, because one epoch or one iteration, how many data points we have over here, right? So let's take, we have 200 records over here. So 200 data points you can take as one calculation unit for one epoch. If that 200 becomes 2 million, you cannot take all 2 million to compute one epoch. Hence, you have to do a batch size, which means either you can take 100 records at one go to complete one epoch and take another 100 records, compute one step like that. So you process in a batch mode. So there are, again, this is another theoretical concept which I'm not going to touch upon right now, because your batch size, whether it is a full batch training, mini batch training, complete batch training. So what is that strategy? How do you introduce it? It's complex. So you need more simulations, more exercises to understand how the batch size impacts, because almost batch size will have impact from all the parameters point of view, right? So which I'm not going to touch upon right now. Now this is simple two features, right? Simple linear features we are introducing. You can reduce the number of neurons by clicking on the minus sign, and you can reduce, because two classes are there. One is the orange, one is the blue ones, right? If I'm going to introduce the non-linearity in the data, so this is my nonlinear feature 1, nonlinear feature 2. This is my interaction feature x1 multiplied by x2. This is highly nonlinear feature using sine x1, sine x2, right? The dotted lines that you see over here, these are having some initial weights, right? You want to change the weight, you can click on this and you can change it. So you can reduce it to maybe 0.002, very small weight you can do, right? The thickness of the line, it shows the strength of the weight. The thinness of the line, it shows very, very small weights. Okay. So so the moment you establish the connection, now click on this, you will deselect it. Click on it, you will deselect. The moment you select, automatically a random value as a weight is being connected, right? The moment you select it. Now, since how many features you have now to train? 1, 2, 3, 4, 5, 6, 7 features now. Primary or basic features only 2. X1 and X2 only 2 basic features. You are deriving another 5 features which are additional. These are like square features. Now, other feature option you don't have over here. In a programming scenario, you could introduce cubic features, that is x1 cube, x2 cube, right? You could introduce non-linearity, multiplicative features of x1 square and x2 square, right? So x1 square multiplied by x2 square, that is another feature you can introduce, which means a highly non-linear, right, or non-linear feature. So when you increase the number of non-linear functions, your total number of features now increases. Now here we have only 7 features, 3, 6, 7 features, right? So there is a formula, how many neurons you need in the hidden layer. This is only one hidden layer. You can introduce more hidden layers, right? So these are more hidden layers. Click on plus sign and you click on expanding the number of hidden layers. So let's keep it simple. I'll just keep it one hidden layer only, right? Or you could just add one more, right? So now 2 hidden layers only. Now first hidden layer, I will introduce more neurons to it. Let's take 8 neurons only for 7 features I introduced. But the basic idea here is the number of neurons in the first hidden layer should be 2 times or more than that of the input features. So if you have 7 input features, it should be ideally 14, right? But in this platform, it is not giving that option to increase the number of neurons. So I'll keep it only 8 over here, right? Now these are all connected weights. Okay, fine. So learning rate, I'll keep it very simple. Let's take 0.01. Activation function, I'll choose only sigmoid. right now. Regularization, I'll choose only L1 because 7 features we are introducing. So I'll keep only L1. Regularization rate, if it is 0, it means linear. So regularization will not get applied. I'll simply choose something different from 0, which is 0.01. This is classification. Epoch is something which I'm not defining, and I will click on play. This play button over here, this is just a start training. Now I click. Okay. Now these are the epochs which are running. Now observe the strength of those lines, those connected weights. Sometimes in the process, you can see the weights are getting refined. Now this is 0.070, 0.73. Now you can see 0.73 also, 72. So these weights will keep on changing based on the input strength, which means the interaction feature is more important in making classification because that is powering the classification right now. However, the faded lines or gray colored lines that you see, the weights are basically virtually becoming 0, which means they have no role to play in making those classification happen, right? It is only the interaction feature which is feeding the classification. Okay. At the same time, you can observe your test loss and training loss. So training error is 0.08. Test loss or test error is 0.12, which means there is a difference. Your test loss is not close to training loss. If that's enough, you want to stop the training, you can put it stop. Okay. You want to place start once again from here. Let's take, you understood right now that X1, X2 is only making impact. I'll drop this feature. What happens? I'll retrain this once more. The most important feature, I dropped it from the data. I'm just using all irrelevant features, basic features, square features, sign features, right? Are they making any impact in the classification? No. It may take more iterations. You could just keep on training it for a longer period of time, right? So which means if you are having one interaction feature and that is getting dropped, it creates problem for the model. So I'll stop it right now. I'll choose a simpler data set. What this scenario happens here. Very simple data set and train. Okay. Almost now you can also figure out what happens here. But again, this interaction feature is dropping here, right? Which means all irrelevant features, because your basic features doesn't have the capability to make this classification happen. That's why you need the interaction features, right? This is only simple data. Now, if I reduce the noise over here, now noise is 5. Retrain this. And sorry, I'm just putting a pause over here. I'll remove this X1, X2 and retrain this. Now what happens, just observe. If your noise in the data is low, you probably do not need an interaction feature, right? Still with 160 iterations or 68 iterations, you can achieve 100% accuracy, almost, for a simpler data, right? The data is very simple. It is already almost pre-classified. Clear? So that's how you will learn that under what circumstance. There are 4 scenarios. There is a circular relationship. There is more complex relationship. There is again circular relationship. There are different kinds of patterns in the data you can observe. With different noise levels also you can observe. You can increase the batch size as well. So play with all those parameters and all the input parameters to the model. So you can use this playground just to understand how exactly it works, right? It's online, it's free. Absolutely, you can use it, right? And before making a code or before writing your Python script, you should play with this. Okay, this is practical. Theoretically, I'm going to share this one. So this is also a free book, which is called Deep Dive into Deep Learning. But you start with this chapter number 3, 4, and 5. 5 you don't have to touch. I think 4. Chapter 3 and 4 is something which you have to cover. Python script is there. XNet is a Python library. PyTorch is a Python library. Tensorflow is a Python library. So these are all compatible libraries. You want to run it in Google Colab, you can click on this. You want to run it in a SageMaker Studio, you can click on this, right? It explains the theoretical part of it. It tells you that how many neurons you need to choose. it tells you, because it is using, since I have chosen here TensorFlow, it is all selected TensorFlow. If you want to do it in MXNet, you can introduce MXNet as well, right? What kind of activation function and how to write those activation functions. So everything is over here, right? So the stepwise method also given here, initializing the model parameters, activation function choosing, and model selection, loss function, training, and summary, right? So chapter number 4, I'm going to share this particular link as well. Let's go through this. Okay. So now you got to know how practically the neural network is implemented using Python, how exactly parameters impact the classification of regressions, theoretically how to productionize it. So productionize it means you have to put it into any one of the frameworks to make it in production, right? You can download it as a notebook. You can download it as a PDF file. You can go to the GitHub to get the code as well. And to get more theoretical descriptions, you can click on the courses as well. So this is a pre-book. Okay. So that's all for today. If you have any questions, and you can ask me.
Thank you so much, Pradeep sir.
Hi.
If participants, you have any queries, then you just put out your query on the chat box.
I think one question is there. Let me answer this question. This is from Tapas Naik. Okay. Is there any specific rule for number of hidden layers to be defined? No, there is no rule. However, there is a rule to define number of neurons in the hidden layer. Okay. It is a function of number of input features, kind of a complexity in the data, size of the data, total number of records, total number of features, total number of records, and the complexity. That will define number of neurons that you would need in a hidden layer. However, how many hidden layers you want to put, there is no rule of thumb for that. That is experimentative. So you can just keep adding. Okay. Fine. So next question from Pranab. What is bias? So bias is a constant which we are adding to the model, which means residuals. So after doing this x1 times w1, and you are deducting that from the predicted result, there is something which cannot be getting predicted, right? That becomes your bias, which is nothing but the error term. Okay.
Sir, another question we have from Satyajit.
Right. So I'll just quickly show what is bias question. In this, we are training the model, right? You can see a small square box here. This is called bias, which means which cannot get predicted, or the error at this node, at this neuron level itself. So each box over here will have this non-linear feature here. Your bias terms will get changed. Now this is 0.01, this is 0.10, this is 0.091, like that, so on and so forth. Okay. Yes. Next question.
Sir, one more question from Satyajit.
Hmm.
He is asking, as we are using black box model, how we can explain those model to end user as per GDPR regulations?
Yeah. So I think there is a long framework for that. So and you can refer to my book. So one of the book I have written over is Practical Explainable AI. So that is the purpose of this book, is to explain the black box models to the business stakeholders. So that's called Practical Explainable. Yeah. So this is the book which I was talking about. because there is no automated system which can tell you whether it is white box or black box. You need to develop or need to use the frameworks which could be used to explain how these decisions are being taken, how these predictions are being taken. Okay.
Sir, good morning, sir. Can I ask a few questions?
Yes, please go ahead.
Sir, my first question is, suppose we have trained a model, we have one existing model with some less data. So can we improve that model later on by adding some more data? Suppose we got in future, we get in future that, or we need to again train from the scratch?
No. See, whenever you get new data, your existing model need to be refined. So what does that mean? So let's take logistic regression. Now you get another 100 records, 1000 records. You add those 1000 records and retrain the model. Once the model, new model becomes better, so you have to compare, right? Compare with version 1 with version 2. Version 1, let's take 89% accuracy. Version 2 is 91% accuracy. So which means obviously by adding new data, your model has improved. Hence, we should use version 2, not version 1, right? And that's how you have to build an automated process for that. As and when the new data comes in, it should improve automatically.
So my second question is, as you told that input features has negative impact as well as positive impact on the model. So,
it may have both.
Yeah.
See, suppose, negative, positive, neutral, all three. Go ahead, please.
Suppose I have so many images. I have to train a classification model. Okay, so to detect the object or something. So some images are blurred kind of thing. So will it put any negative impact, or should I remove this from the training?
No. See, image classification, it has a different connotation. So what does that mean? First, your image need to be converted into pixel values, RBG pixel values, right? So pixels are nothing but the numbers 0 to 255, right? So your image blurring, non-blurring has no impact on positive or negative, because what is going to be impacting is that how you are deriving the convolution layers, right? You are applying convolution layers just to capture the important features from the feature space in order to represent the image in such a fashion that you can train a neural network model. And high dimensional neural network model you cannot do. That is why we are applying convolution layers to reduce the data to a manageable state so that you can apply neural network model on top of it, right? So blurring, if it is blurred, then probably the pixel values would be lost there.
Yes.
Right. Hence, it will not have an impact on the overall prediction process, and there would be misclassification.
Okay. And so next question is, sir, you did some experiment by changing the weight value in that playground. Okay. So how it affects and how to decide that weight value?
Weight value, right? That's a good question. See, currently, whatever demo I have shown you, these weights are being auto-generated, system generated, right? So, which we don't have control, but there is a way to do that, right? So you could take statistical distributions. So you could take uniform distributions, negative binomial distributions, normal distributions, and you can take, there is something called regularized normal distributions, threshold-based normal distributions. So you can generate those weights by using a statistical distribution.
And so then next question, sir, you did some experiment by changing the number of neurons in a particular layer. And you saw that how over
right. So these things, yes. So these things you can run using a grid search, right? So in a normal machine learning, we do a grid search. Similar way, on a deep learning also you have to, or neural network also, you have to introduce grid search. The grid search will take a lot of parameters. Each parameter will have a range of values. It will consider each of the range of the values and form combinations, and for each combination it will train the model, and it will search the entire parameter space to identify what is the best model. So you have to run it in a grid search mode.
Sir, actually another thing I could not get properly. So I think you are telling that something is input layers, the past layer should, number of neurons should be double of input layer, like this you told something.
Sorry, come again please.
No, you told that the number of neurons in the past layer should be double of the input layer, like this some sentence you told that.
That is just a from practitioner's point of view, but there is a formula to it.
But why this double? Why not triple?
Triple also you can take. The more number of neurons that you take, it may have an impact in the training time. If you have large computations like GPU machine, you have access to high definition machines like H5 machines you have on cloud, and you have a budget to run it on cloud, you go ahead with triple, 4 times, 7 times, that is fine.
Okay. And it's depend on the how much computation cost you can afford.
Correct. Computation time and cost both.
Cost. Okay. And sir, my last question is: can you suggest some good source to learn the basic mathematics? It's backbone of
I
this
sent you the
model.
link. I sent you the link. This deep learning D2L.ai.
Dive into deep learning. That one. Or?
I'm sorry.
That you said one dive into deep learning. Some book like you were saying. Send one. Or
Right.
Thank you, sir.
Sir, we have one more question from Ipsita. She is asking, how does the learning rate affect the training of the neural network?
Sorry. Hi. How does
Sir,
the learning
it's
rate affect the Right. So yeah, that's what I have shown you on the same example itself on the playground. See, higher the learning rate, okay. How the optimization happens, that also first you need to understand. So optimization happens based on the cost function or the loss function, right? In the notebook scenario that I have shown you, this is the loss function, the loss value. Like loss after iteration 0 is this is the starting error. Now after 1000 iteration, the error dropped from, like, let's take 0.58 to 0.32. And mostly it is not reducing further. It is sticking to there, 0.322, right? So if you increase the learning rate, higher the learning rate, let's take 10. Now what happens? You can see how fast this is running, how fast the epochs are running. However, if I reduce the learning rate to 0.003, now see, right? So which means the smaller the learning rate, it will take more time to search for the minimum point on the error curve or the loss curve. Okay. Higher the learning rate, so I'll just do a reset over here, right? So let's take, I'll choose different value. I'll do a reset. Now in this, there is small learning rate. Now see the curve over here. This is a curve, right? There is no zigzag point. Versus, I'll do a reset over here once more. I'll use tan H. I'll choose a higher learning rate. Let's take 10. Now see what happens. Due to higher learning rate, you can see the errors are jumping. That's why you can see the spikes here, right? Higher the learning rate, there is a chance that it may miss the global minima point because it experiences jumps. Okay. That is why when you choose a learning rate, the smaller the learning rate, the better it is for the model. Smaller learning rate, you will not see any kind of spike. Clear? Okay. One more question. I could not write all my answers properly. Can we get the recording? Yeah. Okay. Or you can connect me over LinkedIn. Maybe you can put me your questions. I will connect and I'll share the links, corresponding links with you. Tapas, your question is, which is the best cost-effective platform to run neural network? I think local mode is the best. No cost, zero cost. Collab also you can take, run it in a local mode. SageMaker, you have to burn a lot of dollars. Don't go for it. Okay. I think that's all. No new questions.
I think we don't have any further question. Thank you so much, Pradeep Mishra sir, for delivering a talk on artificial neural networks. This session is really an informative one. Thank you so much for being there with us.
You're welcome.
I think maybe the Aditya Kumar, he wanted to share some of his project ideas, so maybe we can give him 5 to 10 minutes before close the session. So Aditya, are you there?
So now we have Mr. Aditya Kumar sir with us.